So I'm Austin Schuh. I'm a mentor on Team 971. We're not here this weekend, but I came down because it's kind of a fun event and wanted to be part of it. So today I'm going to talk about modeling of systems. So we'll start with a simple model of a brushed DC motor, and then we'll take it from there. So I will probably try and go too fast. When you guys have questions, please slow me down and ask questions. Otherwise, I risk losing you guys, and I don't want to do that. So let's start in. So we have DC motor is something where we have two inputs. You have a ground and a signal. It goes into a box, and you get out an angular velocity, right? So we can start to break this down. So what we want to do is be able to model this. So put some equations to this, so we can go and work with it. So a slightly more complicated model is we have our input, and we have a resistor. This resistor represents the windings in your motor. It may be only an ohm or a half an ohm or a tenth of an ohm, but there's still some resistance to your windings. And then from there, it's hooked up to a generator. And then that comes out. Then this is your ground wire. This is a pretty simple model of a motor, but this is good enough for first robots. So the generator, so we want to talk about, so we have a voltage V that we're putting in. And then with the voltage, you also have a current coming in, so a current I. So the voltage drop across this resistor, the resistance R. Does anyone know what the voltage drop across the resistor is? What? V equals IR. Exactly, V equals IR. So this voltage V sub resistor equals I times the resistance of the resistor. So then this is a generator. And so the equation for a generator is the voltage drop across the generator equals the angular velocity times some constant. Omega, we'll use omega for the angular velocity symbol. And then the industry, let me go check so I give you the right numbers. Over kV. So the voltage drop across the generator is your angular velocity times your voltage constant, or divided by your voltage constant. So we can add these together. So the voltage drop across your motor is then equal, then you get V equals IR plus omega over kV. So this says that if we know say the voltage across the motor and the angular velocity and our constants, we can figure out the current, for example. But this isn't enough to actually simulate the system because we don't know how the angular velocity evolves with time. When we apply a voltage, we don't have anything telling us what it will be. So there's another equation that goes along with this. So a motor has an angular velocity and it also has a torque. So a torque is like you grab a wrench and you're tightening a bolt. It's the moment arm times the force. So the torque on the motor, tau, equals, and it is I times kT. So this, empirically, this is saying that the current going through the motor, so your motor is a bunch of windings which make up an electromagnet. So the current going through your electromagnet will produce a magnetic field which will push on the magnets in your motor and produce a torque. So there's a linear relationship between the torque and the current. So yes, KT. These are constants. Actually, that's a great lead into the next question. So I'm going to give you some specifications from VexPro on the sim, and then let's work out what all these coefficients are. So let me pull up the webpage real fast. So we have the stall current. Let me erase something. The stall current of a sim is 133 amps. Yep. And then we have the stall torque. And the data sheet says that's 2.42 Newton meters. And then, is that all we need? Yep. And well, then the last constant that matters is the free speed. So that is, do some gratuitous rounding, that's about 500 radians a second. So your question was, which constant? Actually, we should figure them all out, but.
Yeah, but the KT.
Okay. So we have this equation. So we have the, given a current and a KT, we can get a torque out, right? But say we don't know KT, but we have specifications for a motor. So if we can find a torque and a current, we can compute KT, right? So this is the specs. This is actually enough information to compute those. So what torque and what current do we use to compute KT? Yep. So KT is so it's the stall torque over the stall current, which, if someone has a calculator handy, we can compute this. But you just divide the two and you get KT. Are you backing it out for me? Are you checking it for me, or?
Oh, no.
Oh, sorry, what?
0.018.
And then the units? Somebody?
Newton meters over amps.
Yep. Well, this is not arbitrary, right? So this says to convert from amps to Newton meters, you multiply by that, which is exactly what we're doing with it. So the units actually make a lot of sense. I've seen this equation written out as times KT and divided by KT, so just be careful which convention somebody picked. It's just a constant, doesn't really matter, but you want to be consistent through all your equations. So I picked what I believe is the standard, but I could have inverted it, just fair warning. So then, so now we know KT. So now let's do this, Let's do the same for this equation. So I want to figure out KV. So how would we figure KV out from the same specs?
I'm sorry, omega represents what again?
Angular velocity.
Angular velocity.
So you got to use the free speed.
Okay.
Free speed over.
So free speed, we got 1.
Would that be a 0 current?
Yes. When the motor's spinning at full speed, we have no current.
Yeah.
So 0 times resistance, doesn't matter what resistance is then. So this is 0. We've got free speed. What do we pick for voltage? Well, you pick whatever the spec sheet used, which in this case they rated at 12 volts. So it's 12 volts. So this equals, so V, we can do this V times, or divided by, nope, I stand corrected. It's K V equals omega over V, which, if somebody can beat, this is about 500 radians a second. 41.6? Whatever. And units?
Radians per second over, no. Yeah, radians per second over volts.
Yep. So this gives us, actually we have one more. So given that this is all that they publish, we need to figure out the resistance, right? So how would we do that one?
Well, if we know our stall current and voltage, we can use the V across the resistor.
Yep, exactly. So we can pick the 0 radian a second point, which is when it's stalled, 0, not moving. And we know that we put 12 volts in from the data sheet, and we know what the current that it produced was, so that gives us the resistance. So then V, so R equals V, which equals 133.
0.09, excuse me.
Yep. Ohms. Yep. Sorry, what was your statement?
Well, I'm just saying, like, I don't think we'd be putting 133 amps through this thing in the context of FIRST Robotics. So.
You get pretty close, but what ends up happening is there's other volts. This is from the lead of the motor to the lead of the motor. This is not from the battery to the. This is not from the battery to the battery, right? So you'll have resistance in your wires, resistance in your fuse, resistance in the PD board, resistance in the speed controller to your motor, and then you got to undo that again. So you'll get, I don't know if twice this is a number, maybe 50% of that resistance will then come from the rest of your system. So that's a reason to keep your wire run short. Use big gauge wire from your battery to your circuit breaker and keep that short, because that lets you minimize the rest of the resistance so that you get more voltage to your motor. I mean, we've measured it, so like when you stall it against a wall, measured it at the motor, and we'll see 6 volts at the motor. So, I mean, the same equations then apply, you just don't have as much current to work with.
But we're not stuffing 133 amps of current through the motor, right?
But that's because you have resistance in the rest of your system.
Yeah.
But, I mean, someone, and actually that someone is here, he came, someone went and put these on a dyno and figured out all these numbers, and they put 12 volts in and 133 amps. Now, that's not with a battery, that's with a power supply, but.
You can run 500 amps through that circuit breaker on the robot,
Yep.
just not for very long.
Yeah. Yeah. Okay. So let's start hooking this up. Does anyone have anything they want off this copied down? It is being videoed, so we should have a record. Sorry, or yeah, and any more questions?
No, you have a video and it's going to be.
We're putting it online, right? Yes.
Okay. I'll just get that from you later.
Okay. Okay. So let me put our motor equation back up. I got OKV. Okay. So now we can actually do, if we don't care about current, we can do a variable substitution in here. Or sorry, yeah, if we don't care about current, we can do a variable substitution. So we get V equals, we substitute this in, we get torque over KT times R plus omega over KV. So that's our first equation. So let's start to look at, what would it take to hook this model up to an elevator, for example. So a simple model of an elevator is we have some motor hooked up to, we'll make it really simple. So we have a pulley of radius R, and then that goes to a string to a mass of M. So we could put gear ratios in here as well. It just ends up being a scale factor. So then what we want to do is we say, so the torque on this motor, does anyone know what that equation is? Someone who's taken physics?
Okay, that was first semester. We haven't done
For torque?
Yeah.
R cross F?
Yep. Which will, in this case, since it's it's R cross mg, right?
Yeah.
Or R times mg.
Yeah.
So the torque tau of our motor are the radius of the pulley times the mass times gravity. Actually, we can do this in 2 steps. It's R times the force. And then the force is the mass times the gravity constant. So tau equals R times m times g. So now we can plug this in. Is that our next? Yep. So V equals R times m times g times R. Okay. Okay, and then we have our standard F equals ma. So the force on the motor, or force on the mass, equals the mass times acceleration. Oh, well, plus mg. We should probably just leave gravity out of this. But we'll leave gravity in. It's fine. So we have F minus F equals, no, I don't do this. Minus so the force on this equals the mass times acceleration minus the mass times gravity.
Why are we subtracting mass? Are we lowering this object or raising it?
We don't know yet.
Okay, so then why are we subtracting the force of gravity if we don't know which direction we're going in?
Gravity's always pointing down.
Gravity is always down.
Yeah.
So we just need to find a coordinate system, right? Which is the next step. So we want to say plus x is in that direction, right? Yep.
But
Sorry, what?
that same token, since we're essentially trying to find a tension force constraint,
Yes.
wouldn't it be additive?
And you're right. Good call. Thank you. So the force here is mass times acceleration plus mass times gravity. Okay. So now we have an equation with correlating voltage to, oh, I made it, this is wrong, sorry. We jumped a step. So it's the radius times the force. The force is this, R times plus mg. Okay, so now we can substitute that up in here. Times R plus. Okay. But so now we have something relating the voltage, the acceleration, and the angular velocity of the motor. Now what we need to do is relate the acceleration to the angular velocity of the motor. So what I like to do is get everything in terms of the x coordinate here. So we're all talking about linear units. So pretty simply we can say, so we have the angle of the motor that it's spun so far. If we're in radians, so 1 revolution is 2 pi. So 2 pi times the radius will get you the distance the surface traveled. So we can say that theta equals r times, theta times r equals x. So now we can start, and by the same token, we can say the angular velocity times the radius equals the velocity, and the acceleration, the angular acceleration. Actually, we don't need that. So we got those two. So now we can plug this in here. So we can say velocity. So now we have an equation relating the voltage that we applied to the motor to the acceleration and the linear velocity. So we can, this gets into calculus, but there's some simple numerical method you can use to solve this. And so now we can actually do a simulation of a motor. Yes?
What does that say, that second term?
This one?
Yeah.
This is the velocity of the motor over the radius times the voltage constant.
Actually, I think you may be right about subtracting mass from gravity, because thinking about it, since gravity is always negative.
Okay, well,
upwards or have a positive acceleration, so I don't know. We already have
Okay, let me think about it for a moment, unless somebody else.
If the torque is, if your motor is rotating and pulling the mass upwards, then the grass is going to, and then you're going to have a negative gravity relative to that. And if your motor is pushing downwards, the motor's acceleration will be negative, and thus it'll combine with the gravity.
Okay, so you're.
It should be negative mg.
Yeah,
Minus.
yeah, you were right.
Okay.
So we already have the signs of a relative, just reverse the coordinate system, I think.
Overcome gravity before it starts becoming.
Sure. Okay, we can make this minus x. It's a little bit of a hack, but we'll go with it. Cool. Okay. So, so we want to take this from here. So without going too much into calculus, we can go into that if you guys are comfortable with calculus. We can.
Calculus is pretty cool.
Okay. So, I mean, what's the derivative of the velocity?
Oh, acceleration.
Okay, so we have right here what we have is a differential equation. So we have the voltage equals R times mx, the second derivative of the position, plus mg So we have an equation that takes the voltage in and relates the second and first derivative of the position. So what we can actually do is we can declare more board space. We can actually just solve this we can solve this analytically, but I don't remember those equations quite well enough to do that here. But we can also just solve this numerically since we're on computers. Oh, no, shouldn't erase that. Oh well. Yeah, exactly. You can take this and put this in a state space model, and you're good to go. We're actually, in my next talk tomorrow, we're going to use this model and design, use test-driven development with this model to write software for a robot. And then we're going to put it on Citrus's 2015 robot and try it. So last year I skipped this step, and I think a lot of people wanted to see this. So that's why we're doing that this year. So what we can do, this is it's called Euler integration. So you have some we have some signal here, right? And we have it plotted versus time. And this is, say, a velocity. And our question is, given some initial velocity, x dot 0, what is the velocity here? Sorry, did I hear something? Oh, no, somebody's on the phone. OK, so what essentially we want to, the way this works with the calculus is to get from velocity to position, what we want to do is integrate it. And integrate is essentially we're going to find the area under this curve. OK, so what we can do is we can just split it up into a bunch of little tiny pieces and add them all together. So we could draw a little box here, little box here, box here. What?
Would it be more accurate to use a substance rule in that sense, if you're going off the rectangular?
Yes, I mean, you can make this more complicated. And actually, it's not very hard to do this closed form.
Okay.
But this is, if you make your time step small enough, you'll be accurate enough for first robots. And then at that point, you don't care. Okay. But yes, you're right. There's a whole branch of mathematics about how to integrate functions numerically and try and get more and more accurate. But so what we can do is if we have a computer and we know all these points, we can just take the width times the height of a bunch of little boxes and add them up. So what this means for our equation down here, if we have some initial velocity and we have some voltage, we can keep integrating up the acceleration to get the voltage over time. So we can actually develop a model. And so what this will look like is I'll just work in velocity versus time. So if we have some initial velocity here, and our free speed, switch colors. And our free speed, this is our free speed, is up here. You'll get an exponential decay. So over time, it accelerates up, and then it starts to approach the velocity and holds. And the amount of time this takes is dependent on your mass constant. well, all of the other constants too, but one of the main drivers is the mass constant. Yes?
In my experience, I guess just using accelerometers and using integrators on accelerometer positioning, you get a lot of error over time. Is that like a lot of integrated error over time? Is that a problem with this?
But this is perfect.
Oh, because
We're in a computer,
Yeah, okay.
and we can simulate this to as many decimal places as you have patience for. And we can shrink time to as many decimal places as you have patience for. So we can actually get this very accurate. But with the problem with an accelerometer is there's a bunch of noise, and the integral of the noise ends up being big. Yeah.
Isn't that what the code actually does, where it's like it has like a variable that just it's like a sum, and it just adds that sum to actually integrate?
Yep. Exactly. I mean, that's how you do the integral term in a PID loop. You got something you want to integrate and a slice of time that value is we're going to use that value over, and you just add them up one by one. So I'm sure there are more questions.
is that supposed to be next double dot or just?
I just decided we'd go single dot for here. But yeah, you can just keep differentiating in this and doing this over and over and over. You can integrate as many times as you want. I don't remember what all of them are called. There's the jerk, and then I've lost track of them after that. Yeah. Yeah. Anyone have any questions or places they want to take this from here? Yes.
Actually, I've got kind of a side note. I know we're working with an elevator.
Mm-hmm.
But if you were working with something that was like arm or something where you actually had it, where you were working against gravity, would you end up just having your MA and then you have your MG like sine theta?
Mm-hmm.
Or just keep shrinking that?
Yep. With an arm, you have an angular component to it as well as a linear. But there's a certain point at which you can ignore some of those factors and fit it empirically and move on. It'll just be a scale factor. I mean, you can always do better and better in your modeling, but the trick is to figure out what is the minimum amount of modeling you need to do that will be applicable to what you have. So here, what I've done is I've ignored, for example, the inertia of the motor. So if we're like picking up a stack of boxes like last year, the boxes weigh 60 pounds, and we have a little quarter-pound set of windings geared down 10 to 1, the amount of mass in the windings is so negligible compared to the amount of mass in the boxes that it's not worth wasting our time doing all the bookkeeping on it.
You'd put that in, it would just be, you would have the M plus the M windings? Or no, you have the angular, okay, never mind.
We can explore that if you're interested. I'm out of things to cover, so if anyone has anything they're interested in, we can go that way. So this is one. Sorry, Wesley.
One thing that I would be a little interested in, I don't know if you already covered this, since I wasn't here for the entire beginning, but is building from the differential equation to the state space representation of that?
I don't think we're going to cover that this weekend because not enough people have enough background to follow it. But I'm happy to sit down with you and chat about that. Okay, so we can go over your. So we have the torque on the motor equals F cross force times the radius. But then it'll be plus, we have another torque on the motor, and that's the torque to accelerate up the winding. So that'll be times J times omega double dot. So this is the angular version of F equals ma. It's tau equals J omega double dot. So this is the moment of inertia of the windings, which is effectively the angular mass. Now, if this term, well, F, as we plugged things in, we got x double dot, and we have an equation relating omega double dot to x double dot. So this is just another scalar, another thing in part of your mass term. And if this is way, way smaller than the resulting part over here with your mass, then you can ignore it. So for like a big, heavy elevator and a little 775 Pro, it's not worth measuring the inertia of your gears and the inertia of your windings. You can just ignore them.
So I have a question. Is there like a rule of thumb for loss due to friction on chains, belts, things like that?
I have found in first you can ignore them
Ignore it.
for your models.
Because it's just so.
It's
For gear stages, like in a gearbox, I typically attribute 5 to 10% mechanical losses.
Okay.
So this comes back to the accuracy. So if you want to be more accurate, those are great rules of thumb. For like a 4 or 5 stage reduction, that starts to become more important. For a smaller stage reduction, 5% is probably in the noise. So you gotta figure out how much do you want to do in your modeling. And if you want to be more and more accurate, we can go and we can generate this curve, right? So we can start at some initial velocity, apply some known voltage, and look at the shape of that and fit, model it and compare the two and kind of fit the two to each other. That's a form of system identification. You're trying to understand your system. We've done that too, but that's only if you really care about how accurate your model is.
A good example where you actually should care is if you're using anything screw-driven.
Yep.
An Acme screw, which is fairly efficient for a screw, you're probably going to have around 50% losses.
Yep.
A regular bolt screw, you'll be lucky to get a total of 20% mechanical efficiency out of it. There's a lot of charts you can look up for that kind of thing.
Yeah.
If you care.
Yes.
So you have your model, right?
Yep.
And so what kind of system is going to be in place to make sure that the system actually follows the model? Kind of like error correction.
This is completely open loop. So this is like, if we apply this, what would we expect assuming that everything worked? That's where your PID and those types of things come in. But the really cool part is we can take our model here, we can go hook it up to our PID loop, and go try it on your laptop and see what happens. And then the really fun thing to do is to go fiddle with your model and say, oh, I thought it was 10% heavier than it was, or 10% lighter than it was, and see how well your loop performs. And actually, there's an industry term for that, and that's called the gain margin. It's how tolerant are you to errors in the magnitude of the response. Yeah?
So if you want to use this with a PID loop, say, you would just plug in your measured velocity and then what you want your acceleration to be?
Yeah, so that's a good question. Let's go ahead and kind of set it up. I'm not going to hand solve it, but we all have computers. So we're going to say, so the first thing I want to do here is start lumping terms, because I don't like to write all these. So we'll, how do we want to lump this? We use K1, K2, and K3. So V equals K1. And this is a big constant here, right? That's just K2. K3 X dot. Okay, that's a little more easier to work with. So then what we want to do is say we have our PAD. Sorry, what?
Represents which part of the...
What? K1 is...
that. Okay.
And then K2 is... And then K3 is this part. I'm just simplifying. I mean, in the end, you got to plug all this back in.
Yeah.
But this helps us to write things up easier. So then our PID loop, we have velocity. So the voltage equals Kp times our error, which we're doing a position loop or a
Velocity.
okay. R dot R for our reference dot minus X dot plus K. We'll do KD times right. So we have our velocity error, we have our acceleration error, and then we have the integral term. So now what we can do is we can evaluate what the voltage is for a cycle. We can go plug it in here, simulate this for a time step, and then go plug it back in here, run that for a time step, go here, simulate, just work back and forth.
Could you say those last like 2 sentences?
So what we'll want to do is we're going to have a time step right now, right? So we start out with some initial state x dot. Actually, we should probably just do this in the other order. So we start out with some initial state x dot. We're going to compute some derivative term. We have our error. We have some integral. So we can compute a voltage. Now we can plug this voltage into here. And then we can integrate for a time step. And that gives us a new velocity.
Oh, so what you would use this for is you would use it to predict the response of the
Yep.
system to a PID.
Exactly.
Oh, okay.
And then you iterate the two back and forth, and then you plot it, right?
Cool.
So we're actually going to do this tomorrow. Yeah.
Question. So
Yeah.
Since I'm kind of familiar with this type one, so R prime, R double prime, R triple prime, what are those?
These are, sorry, these are derivatives. So,
Yeah, but
okay, so let me,
what is R in this?
oh, this is our reference. Sorry, I assume things. This is why you should ask questions, because I'm going to assume a lot of things and
I have no
miss.
idea what PID loop is.
So let's go into that then. We have an hour. I don't really have an agenda from here, so questions are great. So R is your reference. It's what would you like your system to do.
Okay.
So just to keep the units the same, R would be a position. R dot is the velocity of our request. We'd like you to be at some angular velocity. R double dot would be the derivative of our request. So if we have a steady state velocity goal, this is going to be 0, because the rate of change of a constant is 0. And then this will be, we're going to take our error. So our request minus our current is our error. We're going to take our error and we're going to add it up. So then that gives you, what you're going to command. So a PID loop is a control loop where you take your error, you multiply it by a constant. You take the derivative of your error, you multiply it by a constant, and then you take the integral of your error and you multiply it by a constant. And then it turns out for second order systems, that's pretty much optimal. I mean, you can do better with some better filters, but for most first robots, that's about all you need. Yes?
What would it look like with the position loop? Makes sense.
Yep. Yeah, you just drop a derivative. Yeah?
You said it works better with filters. Are you talking about like a calendar type
Yep.
filter? Or, okay, so like.
Or a state space observer, or you could do lead lag, or there's a whole bunch of them.
Yeah, you have that. Those filters and you have like
Yep.
frequency filters. And
Yep.
else. Yeah.
Yeah. On 971, we have a couple Kalman filters in there, but it's a lot more math to explain to people, so I don't like to recommend it. We could be here all day with controls math, which is a lot of fun, but yeah. Anyone have any other questions? Do you think if I asked you to go, simulate your elevator when you got home, do you think you could do it?
Not really, because I have my good old second semester calculus. I haven't gotten it.
Well, but we gave you a quick way to sum it up, right?
Yeah.
So the answer is, so we have the velocity, we'll do the position at time 1 equals the position at time 0 plus the velocity at time 0 times delta t. And that's what we were doing with that picture where we were slicing it up. So if we know the velocity at a time step, this is the height, this is the width, this is where we started, this is where we're going to end up. So you can do this in Excel if you want. You can do this in a language, C++, Java, LabVIEW, anything. Now there are better and better ways to do this integral, and you can do this analytically, which is what you would learn in calculus. We can get a closed form solution for what does the acceleration look like. But for most practical things, you don't actually need to go to that level of rigor. Yeah. Yeah.
I don't know. I'm not sure if this is like a relevant or even applicable question, but is there a way to? Actually, never mind. That doesn't make sense. Sorry.
Okay.
When you guys are talking about like filtering stuff, what is that?
This is a rabbit hole we could spend the whole day on. So one form of filter would be we're going to add the last 4 values together. So n minus 3, n minus 2, n minus 1, and the current. Add them together, average them, and return the result. Right? So what this is going to give you is this is going to, large changes are going to get kind of smoothed out, and you're going to get a number. Okay?
So kind of noise reduction type thing? Noise reduction type thing?
Yeah. We can talk about the frequency response to that. What does that do to your signal? That will actually delay your signal. Because if we have, in that case, if we feed a step input in, and then we look at the response, it's going to, the first time step, it's going to be a quarter, and it's going to be a half, 2/3, and it's going to be there. So we're going to get a ramp. Right. Yep, exactly. So the filters modify your signal, and depending on what you want, they'll slow it down while reducing noise, or there's a bunch of different types of them. Yeah.
Oh, I wasn't raising my hand.
Oh, sorry.
Gesture.
You guys have questions?
So we're
Yes,
doing
Rob.
some of this in Simulink
Mhm.
to try and get our answers. Can you give us some pros and cons? I know you and I have emailed.
Yeah.
Simulink yay, Simulink nay, certain scenarios.
So I use Simulink in a limited quantity at work. It's really good at solving differential equations. We could actually, I can write up the Simulink for you if you're interested about how we would solve this. It's really straightforward. But it's hard to get Simulink on a robot. And there's a large, it will do magic for you, and then you won't understand what it did. So we can actually, let's block it out unless someone else has a question. So we need to develop the block diagram for this, right? So we have a voltage coming in, okay? And then that, actually we need to get this in turn, hold on. So we need to refactor this equation a little bit first. So we have a voltage. We want to get something in terms of x double dot, right? So then we can integrate it. And this is actually what you would want to do for simulating it anyways. So we need to get x double dot on one side and everything else on the other. So we have v minus x dot rkv. Oh, no. Okay. Minus gravity, right? mgr r over kt. Yep. Equals okay, so now we need to move this over. V equals, right? Did I get my math right? Okay, we'll roll with it. So then in Simulink, what this would be is we have our voltage coming in, V, and then that gets multiplied by a gain. So we have our gain block. No, R, right? Minus x, oh, sorry. Let's do it this way. Times R1 over. Okay. Minus, this is just a constant, right? Gravity. So minus m3 r over kt. Okay. This is x double dot. Now we can integrate this, which in Simulink you'll see the 1 over s block, which is the Laplace transform of the integral. And then this gives us x dot. Feed it back in there.
What's written on the left triangle on the bottom?
This one?
Yeah.
This is, oh, and I missed a term, you're right. I missed a lot of terms, kt. Over rm. So this is this term right here, right? So x dot over rkv times kt over rm. So let's, oh, it's r squared. So what this block diagram is saying is we have some voltage signal coming in. We're going to multiply it by some gain. And then we're going to add that to a gain times our velocity plus gravity. And then we're going to integrate that. So it's just another way of saying the same thing. But there are tools that can take this diagram and integrate it for you. These are some of the MATLAB products. You can also implement this integral step. I mean, this is the same equation we need to generate so that we can say, x double dot times dt and add that together to get our simulation. So it's all the same equation. You guys have a question? Or? Yeah.
It's not about signaling.
Sure.
But how do you incorporate this with a gearbox and one or more motors?
With the motors, you're just going to, well, we could, I mean, there's going to be a torque out of this motor and a torque out of your other motor. So you can just add the torques. So it's actually pretty straightforward to do that. The gear ratio is going to be a scalar in your torque. It's going to scale your torque up. So if you do a 10-to-1 reduction, you have a 10-to-1 lever arm on your gears. And so you'll get a 10x torque increase on your output, ignoring efficiency losses. And you will get a 10x speed reduction. So then that maps you from your angular velocity of your motor to your linear velocity. It just goes in that equation there.
I've seen friends do this sort of stuff, and I've seen at times when it gets very involved and complicated. Like, well, not that, just doing the simulation, right? What's an example of a system that, in robotics at least, that it would actually get involved in / or complicated that we might have to worry about?
As you add more and more joints to your arm, they actually become coupled. If you do a double jointed arm, they're coupled, and the math blows up so fast.
Okay.
So that's 2 joints. Now imagine 3, 4, 5 joints. It just, I don't think you could do it by hand and keep track of it. Or, I mean, there are people who do that professionally, the kinematics and inverse kinematics of robotic arms. It's a cool class if you're in college. Yeah, there's a lot of cool stuff in this. I mean, you can spend an entire lifetime on this. Yeah. Does that help you guys? Yeah. I mean, you can also put your PID loop in that and try it, or any other various controllers you want to try.
And we've always used the Simulink to give us some base numbers for our PID, and it's pretty darn close to what we do.
Yeah, exactly.
Broken parts.
Yeah.
So you said tomorrow you're going to apply this
Yep.
to Citrus's robot?
Yep. We're going to take literally this equation here. Actually, I think I dropped gravity because I'm lazy. But we're going to take this equation here, and we're going to integrate it, and that gives us a model. And so now we can try and write some software to say zero an elevator and then control it with a PID loop. And the goal is to see how that works in simulation before we go try it on the real hardware, just for the reasons you guys described. We don't want to break the real hardware when we get access to it. Like, say it takes 5 weeks to build it, and you have 1 week to get your software working. It's really nice to be able to start week 2 and work on your software for 4 weeks. And then when the hardware is ready, you're pretty confident in it. This is how 971 develops all their software. We build up models, we write our software, and we go.
Is there any reason, since I remember with the state-space controller, you have the limitation that it has to be a linear system, but in this case, you can just add a sine term. So couldn't you use this as a controller? Is there any limitation?
So this is nonlinear. It's a nonlinear system. So generally what we like to do is try and linearize it. So we try and just offset gravity.
Well, I mean, like, why couldn't you just use this equation to predict what voltage you need to input into the system to get the desired output?
You're assuming you're getting an LTI response out of your system, and that breaks the assumptions that all the controllers are designed with. So none of the math holds to design the controllers.
Okay.
Which is a pain in the rear. So,
I forgot about that.
yeah.
So why do you rearrange that equation to fit
This one?
that?
For here, or just rearrange this?
That.
Well, so let's say we want to then, we have V0, V0, and then we want to integrate it for 1 cycle. We want to take x double dot times delta t equals V1, right? but x double dot's right here. So we can just substitute this in. And this would say, or this would be x, we can say it's x dot 0 equals x dot 1. So then this says that x dot 1 is a function of x dot 0 and your voltage. So this just gives us a direct way to program up our model. Does that make sense? If not, ask more questions. If not, ask more questions.
Yeah, so why not just figure out what your voltage should be and just apply that every loop?
Because the system changes, right? It doesn't actually act this way. It acts close, and so you'll diverge over time. So that's where control loops come in. If our model says if we apply, say, 12 volts for 3 seconds, we'll move the right distance and decelerate to a stop perfectly. But we know in robotics that's never true. If you just turn it on for 3 seconds, it's going to be close. So that's where the controls comes in, where you're trying to correct for where your model doesn't match. Now, if we had a perfect model and it modeled it perfectly, we could just do that, apply the correct signal, and we'd work. But that's not how real life tends to work. Yeah?
We're dealing something with something somewhere that a lot of some of the data sheets have exaggerated figures. Is there any, like, what sort of, I guess, are there any problems with tolerances or differences between the reported constants and the actual constants when you're actually calculating KT and KD?
So it all depends on how accurate you need your model to be. So if your model needs to only be as accurate, say 10% and the numbers reported are 10%, then you're good. If you want to get better than 10%, and they don't always give you these figures, right? If you want to get better than what you think the error bounds are, then you need to start doing your own measurements. And you could go measure this. You can measure all these coefficients, right? And go compute a better one. Yeah. Did someone over in Teammate have a question, or are you just waving your hand around? Nope. Never mind.
So sometimes when you have a system, you have to control, your velocity and your acceleration, right? And in some cases, you want like a much faster like acceleration, deceleration versus like a slower one. How do you adjust your model to fit
Your model doesn't change. What you needed to change is what you're doing. So this is where you change your controller. So where we had, and I erased it, where we had a PID loop, we had a reference position and velocity, you can feed it a nice smooth path to follow. That's called motion profiling. So, but in the end, it's the same physics that applies. We're just going to be less aggressive in the voltage we request to get a less aggressive response.
Thank you for my questions.
Cool. We are nearing the end of our time slot.
If you would plug this into a motion profile, that would be okay.
It just changes the voltage, right? The commanded voltage.
Cool.
So the math still applies. Cool.
So you would need to get it into the above form, right?
It all depends on how you're going to integrate it.
Okay.
And I'm assuming we're going to do this numerically, because otherwise it just gets really annoying. A lot of bookkeeping. OK, I don't have anything else. Thank you guys for coming. I'll stick around to answer some questions if you have any more.
Thank you.